Um, so my name's Margie Turrin. For those of you who don't know me, I'm Director of Educational Field Programs at Lamont. And I have, over the last probably 15 years, worked on a really strong range of different polar projects. And over the last 4 to 5 years, I've worked on this range of projects I'm going to talk to you about today. Three of them have been in Greenland, and one has been in Antarctica. What I wanted to do was share a little bit about what each project was, what were the big takeaways from those projects, and then share with you where we've developed some curriculum and some educational resources for you about those particular projects. So we'll go through things, and I am not in a, I'm the way that I'm watching this, I can't see if you guys have a question. So if you want to just pop in, if you have something that you want to ask while we're going through, feel free to just do that if that's okay. Okay, so I'll start with the Greenland Rising Project, or Galashat Nunat Kafapok is how they would say that in Greenland. So Galashat Nunat is how they say Greenland, and Kafapok would be the rising. And the logo is really kind of summarizing everything about this particular project. As the ice sheet is melting, sea levels around Greenland will actually be falling because of the rebounding of the land around Greenland. So as it's been weighted down by the ice, as the ice is melting back, it will be rising back up again. And in addition, the water will redistribute that's been over the many years been pulled towards that mountain of ice. So it's had that gravitational attraction pulling the ocean towards it. As that ice retreats, that ocean will fall away and redistribute around the world's oceans. So both of those effects will now have the shoreline, sea level falling around Greenland. And that has a lot of implications. And so that was something that we were studying. This was a co-production project, so one where we were working with the Greenland Institute of Natural Resources, which was our Greenlandic partner. But more than that, we were actually working with people in Greenland. So that the whole co-production, while we planned with another science group, which was the Greenland Institute, we actually went into the communities and worked with the community members. And there were a whole lot of people involved. Some of these people are actually members of the community. A lot of our partnerships were with the Inuit, with the Greenlanders themselves. So it was working in three different Greenland communities. And on the map that I have over here, which is very small, I'm sorry, but you can see that those communities were all on the western side of Greenland. So for those of you who are not familiar, the population is really centered on the western side of Greenland. So you can see these, I'm losing my mouse, there we are. You can see these three communities. So Nuuk is the capital. There are about 56,000 people total in Greenland. Nuuk has close to 20,000 of those. So in the 19,600 or whatever at this point. And then just a little bit north of that, we have the community of Asiat. Asiat is just north of Ilulissat, which many of you may have heard of. It's another fairly traveled community in Greenland. It's not huge by any stretch. So we go from those almost 20,000 in Nuuk to just, 2 to 3,000. And some of these other communities, Asiat has about 3,000 people. And then further up, fairly far north, we were in the little community of Kushorswak, which has less than 500 people in it. So we went through very different communities. And so each community that we went into was a different experience, working with the people, working with the groups that were there. So we worked in these three communities, and we had three different project goals in each of these communities, but all of them focused actually on the community itself and the community members. So the first thing that we were interested in doing was collecting data on this local sea level change. And for us, we were interested in, how does this retreat of the ice sheet actually affect the land and the ocean? Like, we were interested in a very academic way, if you will. We were very much interested in the science side of it, but the communities were not at all interested in that. They were really interested in how is this going to affect our lives? And so that was a really important component for us, was to look at it through the lived experience of these people. How would it affect them? Because they are all marine based. There are no roads that are connecting these communities. There are no roads in some of these communities. And so everything is focused on that marine system. And so those small boats are a huge component of it, as are large ships, which are trying to move in and distribute product, bring in goods for these people. In Asiat, they are not a subsistence living community. Kushorshuak is, so they are much more cut off and they have less of the larger ship traffic happening, but they still have large ships coming in. But Asiat has an awful lot of traffic, and the shallowing of their coastal coastal area is going to have an impact on how those ships are able to move in, where they can move in. They're thinking about how to really rearrange their harbor to be able to deal with this. So again, that was just goal one, was going in and looking at collecting this data. The second goal was to do this with the community, so to identify areas that were of local interest, not just where we would pick, but what is it that's important to them. And then the third goal was not only to inform these community members throughout the entire project, but to include them. So it was really a collaborative effort. You'll see through some of the slides that I show you, they were really part of the entire project. So they were part of the project design. Here you see us sitting in a community in the first picture, listening to them talk to us about what do they know about their waterfront. They don't have access to benthic mapping or anything like that, but they fish it regularly and they know the depths that their specific fish. So the Greenlandic halibut is a favorite. If the further north you go, that's a deep dwelling fish. It's a benthic fish, a bottom dweller. So they know their depths. It's incredible what they can tell you about their area. We actually had them participate in the work. So this is Akalu. He was a fisher person in Asiat, and he knew just how to navigate these very shallow waters. He would go right up to these very steep cliffs. He knew exactly where it would either drop off or taper, and it was excellent. He was helping us with getting that benthic information. And then the third thing was we wanted to get their feedback on our findings before we did a final report to them. So we took preliminary results back to them and had them look at them, talk with us about them, help us understand things that we might not notice in the data, hear how it might be affecting them and differently. What were some things that we maybe could tease out that would help them much more in the reports or the findings we were going to share with them. A big part of this was actually talking to the community and getting the community to meetings where we could chat with them. So it wasn't just municipal leaders we were interested in. We wanted to talk to those fishermen. We wanted to talk to the hunters. We wanted to talk to people that were actually using those small boats in the waterways. So we did a whole range of different events. There were culture nights, which is something that they do regularly, where their whole community just comes out and visits some of these locations. We set up pop-up events in the local mall in Nook. So we just literally set up tables and people would just stop by and talk to us. We used a lot of maps to talk to them about things. You'll see here 3 pictures that all show these data maps. They don't get a chance to see this information. They live in Greenland, but this is not something that's part of what they teach in the schools or that they talk about in their communities. And so being able to share in the second image, you can see this is ice velocity, being able to show them how quickly or where the ice is moving the fastest and exiting the landmass. This second picture was actually of the ice off of the land, and that was super fascinating to them. They had no understanding that the land in the interior of Greenland had been pushed down below sea level in many areas by this ice. So that was another fun piece. And then as you go further back, there are others. One is ice thickness and one is just kind of settlements. But this was a great way for us to learn from them. And I think that was one of the key things we wanted to do, was not just go in and impose what we wanted to do, but we wanted to hear what was it that was important to them. We were also able to engage. So this is a graduate student that was visiting from Denmark. She was able to come and participate with us. This was a graduate student that was a Greenlandic graduate student. They were part of this conversation. This was as useful to them. So they were helping us with translation, but also they were learning about how to communicate science to the community, which was a pretty pretty neat opportunity for them as well. So at the first community visit, we just sat down with people and chatted. And in this top left picture, you'll see this is a municipal event. They have a lot of maps of their own that they wanted to point out and focus on things they wanted us to learn or to gather data around so that they could learn more about their waterfront area in this, and that's in Nuuk. The middle one was in Asiat. This was a combination of hunters and fishers who were talking about where they were interested in knowing more about what might be changing in the benthic habitat, because that would affect what they were able to fish. And on the right, we're up in Kushorswak, that very small community. We brought maps and they were pointing out areas where they are actually finding Greenlandic halibut now. And will that change if this water shallows? Will this be, a change in the entire benthic community for them? And here's a picture just so you know kind of what it is they're doing. This is how they live in Kushorswak. These are Greenlandic halibut. You can see they're a really nice sized fish. They're very concerned about losing the Greenlandic halibut because they are a cold temperature fish. And as the water's warming, they're concerned that these will be retreating further north. Even though they are very far north, there's still the Arctic Ocean up above them. So this is Jonas. You can see he's got a hole cut in the ice. Ice fishing is something that they do over the winter time. And, this is him pulling up a whole string full of Greenlandic halibut. So they set those poles and they just put hooks all the way down and lower them, which is very cool. And then these are a group. So they do very little independently here. They like to have group talk. So they would get together and we would have this conversation around a map with all of them there having a little bit of input about what do they really think and where do they think is important, which was fun. It's nice to see that opportunity to work together. And then we literally would end up with these scribbles. Like we would have areas that had, circles around them. We need this. This is representing perhaps where we have caribou. This might be where we're interested in for the Greenlandic halibut. This might be where we're interested in for shrimp. So they have a variety of areas that they fish or hunt and look for different things. And we would take their scribbles and turn them into these polygons. And then we turned that into kind of the maps that we were going to go out and collect data around. So the second visit was actually doing the survey work. And I want you to just take a look at the faces in this community. And you can see that we did very, very heavily focus on bringing the Greenlanders onto the ships and working with them. They needed the employment, they needed the dollars in their pockets, and we needed their expertise. So it was very definite, a real plan to make sure that they were a key part of this entire process. And they were remarkable. I mean, it was just, we would not have been able to get the data we got without their knowledge and their connection to the area that we were working in. We also were really fortunate to be able to bring in some Greenlandic graduate students. So Akaluk, he is a geophysicist that works for Greenland Institute of Natural Resources, had connections to the university in Denmark. And so he brought in these Greenlandic graduate students. And we had 3 of them through the course of the project. Ulak, who then went on to work actually at Greenland Institute of Natural Resources for a while. Jane, who's now working for a mining company, and Nini, who went back for her PhD. So all 3 of them were part of our project, which was so great. And then in addition, we had a high school student who was able to help us. So this is Bilinguk, and we met her in Asiat. So in Greenland, after the 10th grade, if you want to go on to high school, which was the 11th and 12th grade, there are only a few of them in Greenland and you have to leave home. She's from Kushorswak, but she had to go to Asiat to go on to high school. So we met her in Asiat, and she was so excited to hear that we would be working in Kushorswak that she started talking to the team, and they ended up suggesting that she come along as kind of an entry to the community, serve as an interpreter. She speaks English, Danish, and Greenlandic, which is an absolute gold mine in Greenland to have somebody that can do that. A lot of the teaching that goes on in Greenland is in Danish. So Some people are fluent in Danish and English, I mean, excuse me, Greenlandic, but not that English. And so finding someone that can do that three-way translation is really important. Up in Kushorshwak, there is less of the English and Danish, although we did find throughout the course of the study, which went on from early 2020, and we just finished up in August, the students are actually doing more TikTok English. So they have a few more phrases. They have learned a little bit from the TikTok, kind of keying into their phones. So while we weren't able to communicate fluently with them, they did have some phrases and much more familiarity than when we first started. But that would be the youth, not necessarily the adults in the community. They're still fairly Greenlandic language focused. Okay, our third visit was, as I mentioned in the beginning, we wanted to do preliminary results in each community, spend some time there, get a little feedback from them, and hear what they could tell us about the data. So this is pictures of us in these different communities, getting a chance to hear their input and capture their thoughts so that we could improve on whatever it was that we were going to be delivering them in the final form. And then visit 4 was literally meeting with the community. These are 3 pictures from our meetings in Asiat, where we worked with the community. We worked with the harbor master, who's this lovely woman here. And then we met with the municipality. And in each situation, we were able to deliver hard copies of these maps, a digital version of all of the maps, a report that was done in Danish so that it would serve the municipalities better. They are actually less fluent in Greenlandic and in English in Asiat area. Danish is much more their stronghold. So, and all of this was very well received. We also, in each community, had predictions for them that we shared about the changes in sea level. And I'm going to share those with you now as we go through. We had also installed tide gauges in the communities so that they would have more long-term tide readings. The Asia one still functions. The Nook one got taken out, and the Shorshak one got wiped out by ice fairly early on, but we did get enough to help us build the predictions that we were able to share. So the predictions are based on tidal data as well as data from GPSs on the land. And what we found was that in Nook, which is the furthest south, if you recall, the furthest down, you can see it here on this map, sea levels, we predicted that by 2050, sea levels could fall on average by 9 centimeters. By 2100, 76 centimeters. So a significant change between 2050 and 2100. And when I say on average, we did predictions based on the 2 different RCPs. So the most egregious one, the one where things are not put into control, which is 8.5, and then the one that if we were able to kind of bring things under control. So we took the average to present to the communities. So that's Nook. And then these are Asiat and Kushorshwak. So in Asiat, which is more in the middle, you're seeing that we're predicting 12 centimeters by 2050 and 83 centimeters by 2100 of sea level fall, which is, that's almost a meter of sea level fall, which is significant. And then as you go further north to Kushorshwak, you're seeing 22 centimeters by 2050 and over a meter, 118 centimeters by 2100. And you can see why if you take a look at this map right over on the left and see where the ice is sitting now. So there's already been some adjustment going on in Nook. And so that's why you would see this difference a little more softly, if you will. In the Nook area, it wouldn't be as extreme. As you get up to Asiat area, you're seeing that there has been less of this ice retreat already. So you'll see a little bit stronger effect. And by the time you get to Kushorshwak, the ice is still pretty much there right to the edge. And so you'll see a more dramatic effect. So those were the predictions that we shared. We also worked in the schools every visit. We developed an entire curriculum around this, and we developed it in Greenlandic, in English, and translated it into Danish. We worked in the schools. We took them out into the harbor and worked with them around the community. We took advantage of if we didn't have an open harbor. This was a bit of a surprise to us. We were there at the end of May and thought we would have open water in Qushorshwak, but we did not. We had a frozen bay. And so we were going to forego this outdoor, temperature collection and salinity collection in the harbor. But the kids didn't want us to do that. They said, "What about the fishing holes?" So we said, "Sure, why not?" So out we went. And fortunately for us, we did have a fisher person who had made a hole for us. And so he stepped aside with his polar cod for a minute and let us use the hole so that we could collect some data. So again, a wonderful collaboration and a fun chance to kind of just be impromptu and use resources that become available. This, by the way, is Akaluk, who is a real star in this project for us. Um, and then we developed multiple data resources that we shared with the community. So we have a story map that we developed in all three languages. It has an embedded map that has benthic images that can be interacted with in the map itself, so you can click through. We have an entire curriculum, as I said, that's available, and we developed these kind of canvas story maps that were just a physical map that showed the history of the project and some different information about the project, and really let people experience it, which we left in each community. And this is a QR code that takes you to the curriculum. And on the very last page, I'll share with you where all this sits on our website. So all of it's linked into our polar resources on the education resource page. This was one of the classes that we were in. Does it look like your classes, right? They were hilarious. We had such a good time with them. They were really great. Okay, so that's the first. This is our second project. So this one's called the Greenland Lakes Project, and it focused on ice sheet hydrology and these superglacial meltwater lakes. So these lakes that form on the surface of the ice sheet. You can see over here on the left in June, you can see that there's this like surface stream that kind of forms these little bowls, these little lakes, and then there's other streams and another lake. Sometimes you can see those streams connecting these lakes, sometimes you don't. But these lakes have become an important question on the Greenland ice sheet. We've had these lakes along the perimeter for many years. Early maps that we have show them, but they have started to move further into the interior, and we're now really interested in what this might mean for them. For changes in the ice sheet. So this is June. If you go to July, you'll see again, you have these different meltwater ponds, and they've now really formed a strong connection. And then by August, you'll see the one to the furthest to the left, which would be on the ice sheet that's to the west, is emptied. And that's emptied because it literally drained. It drained through a crevasse, a crack in the base, gone down to the bottom of the ice sheet, we presume. And that then could be lubricating the base of the ice sheet. So things that could take, to get this like warmer temperatures to the base of the ice sheet could take thousands of years, whereas this can happen almost instantaneous when these lakes drain. So we wanted to know a little bit more about them. These are the team. This was a smaller team for sure than the Greenland Rising team, but again, also a much smaller scope in terms of a project, but an important one. So again, we have these lakes that form on the surface of the ice sheet, and then they drain down through these channels called moulins that go all the way to the base. And then the idea is that these can lubricate the base of the ice and enhance that flow. So move that ice along in a much swifter pace than would have been it prior to having that water on the base. So they wouldn't have expected it to move that quickly. And just to show you how these things have been moving further inland. So again, this is the elevation of the ice sheet. So the highest the ice sheet gets is about 3,000 meters. We see these moving up, 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 and by 2060, the anticipation is it will be at an elevation of 2,200 meters, which is fairly far in towards the interior. And this is actual data you're seeing. So you'll see these areas where you're having observations of these lakes, and they are definitely moving up, and you're seeing more observations of them. This could be because we're paying more attention to them in this period of time. And it also could be that we're seeing more of them. Again, it's probably a combination of both. And here's a model showing how they are moving further towards the elevated areas, towards the interior, faster, faster. By 2040, we're seeing them really cresting up. So you're really seeing by 2050, there are many more of them and much further into the interior. This is an actual image of some of the study sites. So this study site was actually very close to where the Ossiot community, where we were doing our Greenland Rising project. This was just inland from Ilulissat, which is very close to there. And what we found in this particular project was, so we looked at pockets of lakes where you could see multiple lakes, and you can sort of see there's a connection between some of these lakes, but some of them seem fairly isolated. And what we were interested in learning was, were they interconnected? Does one drainage of one lake lead to changes in hydrofraction in another? And what they found was that there is a connection between these lakes, but it's not always the same. So the drainage of one lake does lead to stressors that promote hyperfracturing, so this breaking of neighboring lake basins. But it also, in others, it can lead to compression, because as it's moving apart, it's pushing the ice closer together in some areas and spreading it further apart in others. So it doesn't affect all these lakes the same way. There are differences in how they interact, but there is an interaction between them, which was kind of an interesting find. We developed a curriculum around this called Eyes in the Skies. It's about remote sensing, because they were actually on the ground setting GPSs, but we use a lot of remote sensing to actually identify these lakes and look at how they drain and form over the course of the season. So that's why we developed something around this remote sensing concept. We use Google time lapse in this, as well as Google Earth, to help students explore different aspects of the glaciers from the remote sensing mannerism. And all of this curriculum is available under this QR code. And it's also linked to the page that I'll share at the end with you. There was also an article about this in the Earth Scientist, where it's been shared more broadly. We've used this a lot. So this was developed kind of throughout the beginnings of COVID. So we had to do kind of a about face, if you will. It wasn't what we had intended to do, but we were able to use it a lot and test it a lot because of that. And then we were able to expand it and do more with it. So it's definitely been tested a lot in the classroom. And I think remote sensing is not something that a lot of teachers feel kind of have a sense of how to dig into. So I think that that's a neat aspect of this curriculum. Also, I don't know if any of you know Alejandro Mundo, who's with Stannis. He's a New York City rep, but he worked with us on a research experience for teachers in RET. And he developed this really great story map called Polar Perspectives. And it's around this project. So he has a climate change module, then he has an Arctic-Antarctic module. He has one that goes just into Greenland. And then the ice tracking and changing, that is all focused on this project. He's got a lot of data in here. It's a really great opportunity. It's got worksheets that go with it. So it's a great opportunity to actually share this project. He did a beautiful job. So it would be lovely to get more teachers connected with that and sharing that. Okay, project number 3. We're stepping through. So this is Green Drill. And Green Drill was a very ambitious project that's just wrapped as well. This one was looking at how sensitive is the Greenland ice sheet to climate warming? And through this project, the goal was to drill in four different locations around Greenland. It had a large group of people involved with it. Uh, it was one that involved bringing a large drill that had never been used before actually in the field. So well, excuse me, it had been used in the field. It hadn't drilled this deep in the field. So there were a lot of like testing, pushing the limits, which was pretty exciting about this. It was also a kind of a unique opportunity to look at a transect of data. So each one of these locations was going to have a transect of three different drills using three different types of drilling. And each one would be drilling from the rock off the edge of the ice through a small thin section of ice with a winky drill, and then through a much deeper piece of ice using the ASIG drill, a much larger drill, which I'll show you a picture of. And through that, they wanted to kind of look at the history of the ice sheet. What they were focused on was they're not focused on the ice itself. They were focused on the actual changes in the rock beneath the ice. So they had to get through the ice sheet to the rock below. And they needed a cold facing bit of ice. So they needed where there was a cold bottom on the ice sheet, not a warm one. And a lot of Greenland has some kind of warming at the base. So they were very carefully picked these locations so they would get that cold base of ice so that they would really see the true data. It wouldn't have eroded or been moved. Prudhoe Dome was their first location that they went to, and Prudhoe Dome is this little spot on the top on the western side. And I will show you a little bit more about it as we go. So these are the three different drill locations. You can see this is off the ice sheet. This one's going through about 100 meters of of ice. And then this one was going through from 300 to 600 meters of ice. This drill had never been tested through that much ice, as I said. So that was kind of aspirational. And here's a graphic that we had drawn about the project. And you can see this. This is the drill with the tent. This is their little tents of the researchers themselves. And you can see this drill going straight down through the ice. So the challenge when you're going through ice of that depth is that you'll shear off the drill in here somehow. You'll have a breach. And it was very problematic for them. They had a lot of challenges. And this is where I introduce our Greenlandic mythical creature, the Kivitak. So the Kivitak is believed in Greenland to bring bad luck, is a harbor of problems, of challenges. And this project had Kivitak in spades. Everything they tried to do, Kivitak showed up and said, no, you will not. They had one challenge after another. They thought that everything was, completely for naught. They were not going to be able to penetrate all the way through. All the lead scientists had left and left a couple of grad students behind with the ice drillers just to see if, they could help with the cleanup. They were frustrated, but, they had learned a lot in the process. So it's never a lost cause. You've always learned something as you go through the project, and they learned a lot, took a lot away. But as it turned out, they banished Kivitak, and they did manage to get to the base. But let me show you kind of the conditions of setting up this. It was just horrendous. So you can imagine trying to put together a tent, put together a rig in these conditions. I know I remember Jörg saying when he was going up, and Nicholas had already been up there for a while, Nicholas Young, and he said, bring everything you have, every piece of clothing you own, because it is colder up here than you can imagine. So yeah, it was pretty uncomfortable conditions,
What
but
were
they
the
did.
winds? What were the winds?
I'm sorry, I don't know the winds at this point, but the winds were quite significant. So there were katabatic winds, and you guys, I'm assuming, know that, on the ice sheet you get these really bad katabatic winds. I don't know. We can find out from them another time. I wasn't there. For this one, I wasn't there. I've been involved in most of them, but not that one at that level. Okay. So key achievements were that they set up two camps, not just one in Prudhoe Dome, but they set up two. Oh, I see that the E got pulled off of Prudhoe Dome, but that should say Prudhoe Dome. They set up one where they could use the Winky drill. And remember, the Winky drill is able to go through 100 meters. So that would be off the edge of the height of the dome. And then the ASIC drill, which is what you're looking at right here, this massive drill, that was designed to go all the way through. They did manage to get through at the very last minute. They got 509 meters down through the ice, and they got to the base, which was unbelievable. And that was the two grad students, so Allie Balter Kennedy and Caleb Welcott, managed to actually be there when this happened. I think for them it was like this was a great launch to their careers, right? I mean, you can't be more excited about the opportunity to do something like this. So that was pretty cool for the two of them. And they both were just finishing up and have now moved on to, positions elsewhere. They're not where they started when they were in the project as grad students. So that's pretty cool. And in terms of findings, so Prudhoe Dome is a fairly decent size, 965 square miles. And they found from this that it was fully gone. This Prudhoe Dome was fully gone. There was not ice here in the period about 7,000 years ago. So they were able to date that far back. So that tells them that this sensitivity of this particular area is about 3 to 5 degrees C warmer than today. So that was an interesting finding. So again, one of the things they were mainly interested in were where were the most sensitive parts of the Greenland ice sheet? Where would we be seeing the melt coming from the first? So again, remember this was way over on the west hand kind of corner at the pinnacle Prudhoe Dome. So they found that area is more sensitive, is highly sensitive. And Nicholas has been working kind of across from there in Baffin, and they're finding a comparable thing over there. Although I don't want to speak for Nicholas and his project, but pretty cool. So this is some of that rock that they recovered, which again was very cool. That particular project, by the way, we developed, I didn't have a QR code for the curriculum, but there is kind of an exploration using a Greenland map that kind of takes you through their different project sites, the different drills, et cetera. And that's linked on that, as I said, the last page that I'll share with you. Okay, the next project, I'm going to shift to Antarctica for the next project, and then I'll come back to Greenland for the final one. But this was at ITGC, which is the International Thwaites Glacier Collaboration. Thwaites is this very sensitive area in this little red box. I hope you can see that. But it's in the Amundsen Sea area. So the peninsula area of Antarctica is the more sensitive area to change. I see somebody just put a chat in. So there's some granite is a big component of that rock down there, Richard. So sorry, you're talking, we're going back to, I assume, Prudhoe Dome. This area is the Thwaites section of Antarctica. Again, Amundsen Sea area. This is an area that's fairly sensitive to change. So the peninsula area is more sensitive than East Antarctica. So East Antarctica is sitting high up out of the ocean. It's sitting up on bedrock, whereas West Antarctica and the peninsula are more like an archipelago, and they have pushed in many areas well down below sea level. So this area is much more sensitive. The area of Thwaites has been found to be changing very dramatically recently, and as has Pine Island, which is just to the to the north of it. And this is an area where the shelf, the continental shelf, is actually fairly narrow. So the ice is close to the continental shelf, so you're getting warm water coming up over the shelf, and that water is actually getting up underneath the ice sheet itself. And the concern about Thwaites is that while it is itself sensitive, it's a large shelf and there's a Thwaites Glacier, it's actually connected into a large section of West Antarctica. And so it will cause the evacuation of more ice than just the Thwaites Glacier itself. What I wanted to focus on, sorry, I think I keep seeing things pop up, so I should, or
We have one
nice.
question
So
about what kind of rock in Greenland
So
did they
there's, yeah,
discover?
I see those. It does look like felsic granitic rock. I would say it probably is. I am sorry, I don't have the geology map in front of me of that particular area. I know they're very the when they do beryllium sampling, which is what they were doing on this. They also did luminescence sampling. I don't know if there's two different types of ways that they were looking at in terms of um, how to actually date that rock. Beryllium is something where they really need a fair amount of, well, the best results are when they have a fair amount of granite. And so that's why I went to granite as a component of it. And I know that it did have a fair amount of that in it. That is, so with beryllium, you're capturing cosmic rays when it's exposed to the atmosphere, and that changes the signature and creates this isotope beryllium-10. And that is what they're looking at, the accumulation of that. And so that, again, was why I went to that. But I can't do any more in terms of helping you identify that. I'm sorry. We could find out and get back to you, but I don't know any more than that right now. So to kind of go back to Thwaites, I thought it might be interesting to look at a couple of the interesting and novel tools. By the way, I don't know if you all are following along with the New York Times, if you look at the New York Times, but there's a follow-on study to Thwaites. So Thwaites is just wrapped in terms of field week. We're still finishing out with papers and working in the lab. And so the end of this project is coming up fairly soon, end of March, if I'm not mistaken. But there is a follow-on project that's already launched that has more researchers going down there. One of the things that we really were interested in was that there would be a follow-on to this, because we found, and this is often the case, way more questions than answers when they were doing this research. This was 100 collaborators as part of this project. There were many nations represented, but the two main partners starting were the US and the UK. Then we got Sweden involved, and South Korea came in and really helped tremendously because they had the ability to bring in a ship when the US ship was no longer available, and the UK ship was being launched in the immediate future but wasn't available. So we used the South Korean vessels to I shouldn't say we used them. We worked with them, and so they supported some of our scientists. They are the ones leading the new expedition. So it's South Korea with many partners. The UK still has a partnership. So this is one of the things that's so great about working in some of these really hard to reach regions, is that collaborations are really a big piece of them, and it gives you a chance to work with scientists from around the world and learn together and share resources and kind of make more happen because there are more opportunities. So the instrument that you're looking at here is IceFin. IceFin is Brittany Schmidt was the one who developed this, but Brittany will always say it was Brittany Schmidt and her students. She was at Georgia Tech when IceFin was developed. She's now at Cornell, but her students are a key part of what she does, and she always wants to make sure they're given credit. So this was an instrument, is an instrument that goes down. So they cut a hole. I don't know if you can even see that hole, but there's a little hole in the ice right there. They've cut a hole there, and then they're going to deploy IceFin down through that hole. And so I'm going to just run this for you so you can see how they haul it up, haul it up, haul it up, restructure it, set it up. So this is a tethered AUV, so it's on a tether. It's actually not just going to free swim down there. It's going to be controlled by them as it goes down through the ice sheet. So they're ready to go, and we now have um, some footage of it actually going down the borehole. So this is it going down the borehole, which is kind of cool. So they went through 600 meters of the ice shelf. So that's that floating section of ice that comes off of the main ice sheet itself. It's connected to the ice sheet on the backside and on the edges, but it is free floating. And so it's a really interesting area because it's exposed to the ocean below and therefore is much more sensitive to changing than the ice sheet itself, which is tucked back away from the ocean for the most part. And so they're very interested in how that water that's underneath there might be eroding away on the ice. There's a section where the ice sheet meets the ice shelf. So that is where we call the grounding line, where it goes from being frozen to the bed to actually going afloat. And they were very interested in getting back to the grounding line to really understand how the changes are happening. So on the right, you see a picture of ice fin. I don't know if you can make out the fact that this is tethered. Do you see that little line there? So it's actually being connected and controlled from up above, but it has a camera. It has instruments that are measuring salinity, temperature, a variety of different things. And it's helping us just kind of probe this particular area. So this was Iceman's first venture out in Antarctica. So that was the first of these three cool tools. The second cool tool was an autonomous unmanned underwater vehicle. So something that was not tethered and was released to go underneath the ice. So this came from Sweden. They called it RAN, which is the name for the Norse goddess of the sea. And this was run by our Swedish collaborator, Anna Wallen. Large, 7 meters long, right? So a pretty big, it's like a little submarine, basically. And it's just filled with technology, all kinds of sensors. This runs, however, without being tied up. So once you deploy this, you have some communication with it. You can try and control it a bit, but you can't guarantee that you'll always have connection to it. So they first took it down in 2019 on the very first trip, and the goal was just to see if they could get it in the water and get it to respond and move around. But you know, a scientist is always going to push the limits. So when they got there and they had really great access to the front of the ice shelf, and Anna got this thing in the water, she was like, let's just do it. And so she sent it underneath the ice shelf, which was never part of the plan. But it was a remarkable opportunity. It was a remarkable success. She got back really interesting data. So by being able to kind of let it go on its own, there's a little bit more of an area that it can travel than Icefin, which was tethered, right? And you couldn't control it. You couldn't let it go as far. It couldn't roam as far. So that was really exciting. The plan was it would come back another time. The next time that the ship was in, they just couldn't get in as close to the ice shelf. They actually couldn't get into Thwaites at all because of all the sea ice that was there, the floating ice on the surface of the ocean. So they went into an adjacent glacier, Dotson, and studied that just to see about interactions between the two. So you never come away empty-handed, but you might not get back what exactly you were hoping to get. But she did manage to get it back down again and edit out. So in 2024, Ron went down again and did do a couple of cool dives, but unfortunately, the last dive it just didn't come back. They waited, they brought in helicopters, they used acoustic, they tried everything to try and get this back. It's a fairly expensive piece of equipment. But yeah, they never managed to get ran back. So We could just say Rand gave it all for science, I guess. So this is one of the challenges when you don't have something that's tethered to you. There is the opportunity to actually to get just disoriented, run out of batteries, and you just or it gets lost from communication with you, and it just goes off on its own. So we did lose Rand, but it was a cool tool while we had it. And then our final cool tool was the seals. So there were a series of seals that helped us in Thwaites. This one's a Waddell seal, very cute, right? We use both Waddell seals and elephant seals. There's an elephant seal. The elephant seals are a little bit larger, as you can imagine. This guy is like almost 8 feet tall, 750 pounds. This is Lars, like trying to make himself big so that he can make sure the elephant seal kind of keeps its distance. Of course, this is all done with so Lars is a trained biologist. There's a lot of licenses and special permits required. But the goal was to actually put some monitors on their heads. They would glue them on. They pop off at the end of the season when the seals molt. So it's not a permanent thing. It does not interfere with them in terms of their diving or anything else. Elephant seals can go very deep. They can go under 800 meters down. I mean, they really can collect some cool data for us. And they're free swimming. So they will go places that we might not think about going. So again, each one of these has kind of a unique plus and minus to it, if you will. You can control where some things are going. You can't control where other things are going. But you get a whole range of different data when you have this down. And we got some really great data from our seals. So we had 4 seals. We had 6 seals, I believe. Two of them we didn't get a whole lot of data back from. There are 50 seals down there just, collecting data for a variety of projects, but we didn't have 50 ourselves. You can see the little monitor on his head, so the little instrument where once he comes up, he transmits that data back to a telemetry, and we get the information. And they did over 1,000 dives in this first week, and they collecting ocean salinity temperature data. Lots of really cool information came back on 94 of those dives. So they were really down there, like I said, 800 meters deep with the elephant seals. So very, very cool. So those are our Thwaites kind of cool instruments. We had an awful lot. We had 8 different science projects. I could spend a whole, session just talking about Thwaites, which I didn't. I wanted to share these other things. So I won't go any further into Thwaites, but very cool project. Keep your eyes focused. I will tell you some of our findings before I step away from it, but keep your eyes on the New York Times because they are doing a really good job of covering the follow-on. So implications for the future from this particular area. The first is first of all, I mentioned here's Thwaites, here's Pine Island. As I said, this is the Amundsen Sea in here. There are a whole range, Dotson Cross. There are a lot of different glaciers in here that, again, are kind of all interconnected, and they all tie into this deeper interior of West Antarctica. And these are the 2 areas that have the fastest flow, and this one kind of coming close behind. So first key finding was that this ice shelf, the front of it, is really near breakup. So there's been a lot of breaking up. Our last on the ice projects were severely threatened by all the breakup that was going on. But because we did not have a helicopter on the ship the last time we went down, the South Koreans did. So they were able to get some of the people out on the ice to collect closer to the ice front. We were able to get our scientists a little further back and kind of look at flow and change, but it's definitely breaking apart quickly in the front. Another finding was that these robotic vehicles really discovered kind of new melting processes that were going on underneath the ice shelf. So there's this kind of scalloping that goes on, and in areas where you have a scalloped edge, you see a lot more melt going on because that's kind of sitting down, and so it's more in connection with that warmer water. We're seeing that this tidally driven seawater that kind of gets up here, so it gets up underneath the ice shelf. So you can see it kind of getting pulsed in as the tides move. This shelf kind of responds, and you get this warmer water going up underneath, and that's really hastening all of this melting and impact. Um, we we saw evidence that the seabed, so from material that they collected from the ship and cores, that in the fact it's retreated episodically in the past more quickly than we're seeing it now, which was interesting. That the modern ice retreat started about the 1940s, which was very interesting. So they were able to tie together some different information to see that happening, and it was very much correlated with the Pine Island Glacier, same timing. So again, the 1940s, that the past recovery from thinning, so it has retreated and then regrown. That took, several thousands of years. And then there was a lot of really cool data that was put into modeling. So two of our programs were modeling programs, and the other six were more field programs. So the modeling programs were waiting for the field programs to feed data into them. And so that was kind of a cool aspect of it. So a lot of cool stuff came out of it. But again, a lot of questions arose, and that's why it's really great to be able to partner with the South Koreans. South Koreans have a commitment to be back in this area regularly for the next, I think it's 5 years, if I'm not mistaken. They're really committed to studying this area, which is great. Okay, and speaking of it being great, we'll talk about the GREAT project. So this is the Greenland Rate of Ice Sheet Retreat. So trying to look at the past. This is the final project that I'll chat about. And this is one where we're looking at the Holocene. So we were looking at this last 11,600 years, this current interglacial, and looking at the history of Greenland's ice sheet change through the Holocene, and using that to kind of build models of the future. So we have a multiple array of proxies that the scientists were using in this. And then I also mentioned that we built some middle school and high school curriculum around it. But I'll tell you a little bit about these proxies. So the first proxy you see here is from glacial lakes that are called threshold lakes that are right on the edge of the ice sheet. So as those lakes they're formed because the ice has left a depression when it starts to melt back. So there's a low area and the ice pockets there. And these threshold lakes can tell us when that ice sheet retreated back, because the very bottom of that lake will be glacial clay that is material left by the ice, the ice is grinding over the bedrock and it's leaving this glacial clay, glacial flour behind it. So that's the very base. And then once the ice sheet has retreated and pulled back, it's now opened this area to organic material to blow in. And so then you get a layer of organics on top of that, which is called gitcha, which is just very organic, rich material. And so by taking a sediment core from that lake and looking at where those layers of glacial clay and organics are and dating those organics, you can get a date on the ice retreat. Interestingly enough, we find that there's kind of, in many places, the ice expands and covers it, then it retreats, then it comes back, retreats. So there's kind of hiccups in there. Beside that, you'll see a dinocyst, which is the kind of a seed pod, if you will, of a dinoflagellate. So they release these pod spores, and those go down to the bottom of the ocean. They sit there. If the conditions are right, they'll return as a dinoflagellate in the next season. If the conditions are not right, or if that particular one is just not going to be viable, they can then fossilize and become part of the history and the sediments. And we can look at those. They carry a whole lot of information for us in terms of what was the temperature, was there sea ice there, a whole range of understandings. The third is the rock sampling, so the beryllium again. So looking at beryllium to see when the ice was first retreating from that area. Then we have a very cool polytrichum moss, which is an organic, and that tells us the opposite of when the ice was retreating. It tells us when the ice moved into this area, because it will immediately kill this moss. So we know a kill date, if you will. over here, you see an ice core. So we used ice core data to kind of tie into the history around the different parts of the ice sheet. This is looking at leaf wax data that is found in the surface of the mud. And then the last one was looking at, this is very cool. This is looking at these terraced lakes that form as sea level changes on the edge of the Greenland um, land. And so as the ice is retreating, the land is starting to rise, and you get these lakes that were marine embayments that now become freshwater lakes. And you can tell the history of sea level change by the different, when that went from being a marine to a lacustrine or lake environment by those little macrofossils, which is pretty cool. Okay, so you're not going to go for me? There you go. So just a reminder of the Holocene and how dramatic that change was. This is a graph from the Gisp ice core. So the Gisp ice core is right in the dead interior of Greenland from the summit area, Gisp 2. There are several other, there are not many others, but there are several other really good ice cores that are around Greenland. And we have looked at data in this project from all of them, but I'm just showing you the Gisp one. So basically, you can see, boom, at 11,600, you see this really dramatic change in terms of warming. So what we're looking at here is a graph that goes from 13,000 years ago up through almost present. And our anomaly, so the temperature we're comparing to is this pre-industrial temperature, which would be our zero line. And so you're seeing what changed in comparison to this pre-industrial baseline that we're looking at. And you'll see that it prior to this Holocene kickoff, Greenland was about 15 degrees C colder than it was as it emerged into the Holocene. And you can see, so this, you'll notice that if you look at a contemporary graph, we will see a dramatic uptick here. This is something that I want to make sure that is clear to people, that this data actually stops around 1850. And the reason for that is when you collect an ice core, often you don't get that top amount of data. So this ice core went through 1850. If you want to get that top section of data, you usually get a much smaller section on the top because the surface of these longer ice cores can get damaged. So this particular one goes to 1850. So you can see that this is, which makes sense why it's almost on the baseline there, right? Okay, so we're looking at this period of time. And we're using proxies. So again, proxies are things that stand in for something else where we don't have a direct measure. We can use some other method of collecting an understanding of that period. The Earth collects a lot of proxies for us, and this particular program focused on the Earth proxies that it collected. There are other kinds of proxies that you can use that are not just a direct measure of the Earth. Sometimes we consider like historic weather logs as proxies. So again, there are different types, but this one was looking at, as I said, these ice core, different ocean fossils, et cetera. But you can also use tree rings if you have tree rings. Clearly, we didn't have tree rings in Greenland because there aren't the trees there to provide them. But so we used other things and looking at the history of the ice sheet. And here's that temperature that I was mentioning to you that we're so used to looking at. So if you go to the last 2,000 years, you see this really incredible spike. So one of the things that I think is really important to mention about proxy data is that it has pretty large error bars on it. No proxy is perfect. And I think that that's a really important takeaway. However, the more proxies that you bring together, the better, the more you reduce this uncertainty. So the more that you can really narrow this. And so by bringing together all the proxies that we looked at in this particular project, we were hoping to reduce all of this uncertainty and get a better sense of what was going on in the Holocene. And out of the, so this is a two-phase project. The first phase ended in 2020, and then we're just kind of wrapping on the second phase. So out of the first phase, we just looked at the southwestern corner of Greenland, that area where I was talking earlier about how we've already seen some pretty good ice retreat. And in this particular area, focusing on that, it showed that the rate of mass loss from the Greenland ice sheet is going to exceed Holocene values this century. So it was showing a much more accelerated rate than what we'd already seen in the Holocene. And you guys just looked at a graph and saw that there was some pretty significant change that occurred in the Holocene. So that's a pretty strong statement. But that's what the data was saying from that southwest section. So then the goal was to take this and extend it around the whole of Greenland. And that's the phase that we've been working on now. And that particular challenge is a little trickier because there isn't as much exposed bedrock. There aren't as many proxies available for us to look at around all of Greenland because remember that particular area in Southwest is an area where we have more exposed rock and land. Another thing that we wanted to talk about in this project was the role of a field scientist versus the role of satellites. And so part of the curriculum that we developed was really having students think about, what can satellites do and what can scientists do and how do they work together to give us better and stronger information. And I think that it's important for students to understand satellites are not going to replace scientists. We still need scientists in the field. We're still ground truthing data with scientists. In fact, we're in a project right now where we're trying to ground truth some Greenland Greenland ice sheet data using ice, people just collecting snow data for us up in the Catskills and the Adirondacks to help us understand snow water equivalent and albedo, et cetera, from the snow there, which then can help us with what's going on in Greenland, because most of our snow data actually comes from the west coast of the US, where it's a much different kind of snow. So again, people are important. Scientists on the ground are really important. Also, satellites only can see so far into things. They really, ocean temperature, they're looking at the very top of it. So we still need people and buoys and other instrumentation to really help us. So again, just an important thing for them to be familiar with and think about. So we developed a curriculum, and that curriculum starts out with a fairly simplified slide presentation. Some of the slides I showed you are part of that, and then there are other ones that get the students thinking about the Holocene and familiar with proxies and what are some of the things that we're going to focus in on. And then it's set up with 5 different stations. And the way that I used this with Marist undergraduates last week, and it was super successful. We've used it in high school classes and in middle school classes. It is one where I've done it where we break the student groups into 5 groups. They each pick a scientist. Their scientist has a packet of data. All these scientists collect different types of data, so the data they're looking at is very different. They're looking at a different concept, a different proxy, so that they need to read about the proxy and understand it. Then they try and do some data interpretation. Then they talk as a group amongst themselves with each scientist. So if they were studying Estelle and she was looking at Dionysus in the bottom of the ocean, there would be a group looking at Estelle, talking about it, and then they would have a conversation to make sure they understood what Estelle was doing and talked about the proxy. They talk about the weakness in the proxy, which they will have to come up on their own. I don't give them any information about the weakness in the proxy. I think it's kind of fun for them to try and think about what could go wrong with this proxy. And then once we've got that group solidified, then they split up and get into groups that have all five stations or all five proxies represented, and they share with each other about the different proxies. So what did they learn? What was their scientist doing? What did that scientist learn about the Greenland ice sheet, which is one of the questions on their worksheet? And then talking a little bit about the proxies and their weaknesses. And then we bring it all back together, and we bring it all back together with Josh, who's the modeler. So he's going to take everybody's data and he's going to look at it. So these are the five different scientists that they're looking at. Harley's the one that's looking at those tiered lakes and looking about sea level change using the different macrofossils, whether they're lake or whether they are marine. Nicholas is looking at the beryllium sampling, looking at when the ice moved away from the land and it started to collect cosmic rays and start that isotopic clock. Estelle looked at Dynasys. She was looking at the sea ice history along the edge of Greenland. Aaliyah was looking into those threshold lakes that are right on the edge of the ice sheet to look at when they went from this inorganic glacial clay to this organic mud. And Liza was looking at the polytrichum moss and when that was actually frozen by the ice moving over it. So they each have a station. Nicholas is looking at building the retreat of the ice sheet by the exposure dating, as I said. And one of the cool things that comes out of that is that 8,000 years ago, the ice sheet was actually smaller than it is today, which is kind of a surprise to most people. It didn't just tip state back in time, it had a retreat and came back. And that, by the way, is a very hard thing to date because you erase a lot of that data when you move over it. This is a little video of being up on a moraine in Greenland. So this is the work that Nicholas would be doing and collecting exposure dating on. We hiked up on top of this moraine. You can see the ice sheet in the distance and just had a chance to kind of get a lay of the land. Those little meltwater lakes, right? These threshold ponds that form as the ice sheet retreats. You can see these little ponds form and collect lake water. And that's the kind of lake water that Aaliyah would be collecting those sediment cores from. This was my first experience flying a drone. So you'll see me over here somewhere, maybe. Oh, maybe I'm going to be out of the picture, but wait, here she comes. Don't miss me. There I am. Boom. My big adventure in droning. And then, as I mentioned, Aaliyah was taking these samples. So the students would get a sheet like this. They would see Aaliyah as a superhero. They would see a core like the one she collected. They'd see where she collected data. They'd see her out on her little pontoon boat. So this is the boat that they take out into the lake to collect that data. And then you really can see beautifully in this particular core that glacial clay on the left-hand side and where it goes to organics and it's got this nice rich mud and different kind of layers. You don't see much layering in the organics. I mean, the inorganics, it's just all kind of a blob of gray, but you really can see these very cool layers in this other. I'll play this for you too, so you get a sense of they're out on the lake. So you can see the beautiful color in this lake. That's the glacial clay that's causing the sun to kind of reflect off it, and it has this beautiful blue color. But you can see it's a murky blue. And they are trying to collect a core. We would assemble this pontoon boat when we're out in the field. You put the planks on, you put the A-frame on, here comes the mud. And this does not have its own motor, so you see a little Zodiac with a motor behind it. They pull this up and they bring it over and make sure it's all capped off and it's going to do what they want it to do. And then again, this is Carly. So just an example of some of the materials that the students would work with. And it's kind of fun for the kids to know that they actually find these old jellyfish, like a really a remnant of a jellyfish in the marine sediments from the bottom of these uh, tiered lakes, which is very cool. And they're finding, caddisflies and things. So it's really kind of fun. This is data from Carly. So, and these are kind of the tasks that the students, this is the middle school version, the high school version. It's a little bit more in depth than this. So they read about it and do a little bit more with it. But you can see these different layers. So there is no marine sediment in this top one. So we know the marine limit was at 58 meters in this tallest threshold lake. And then, as you can see, there was a step here where it was at 47, then at 40, at 26, 13, and now we have this modern day sea level. And so there's a key here, and they do some data interpretation with this. And it's, again, a very different kind of data. So some of the data is graphs, some of it is graphics like this with data embedded in it. Allies has different cores that have different dates on them, and they have to do some interpretation. They're all very different. This is the high school sheet on the left, and this is the middle school sheet on the right. So just so you can see, there's a little bit of a difference in terms of what the students would be doing. I want to play this from Josh, and I realized that I had not turned on my sound. So if you don't mind, I'm going to reshare and turn on my sound this time so that I can play this video. So Josh, when they come back together, Josh kind of ties it all together for them. So this is like 3 minutes. It's not very long, but it's really very cool. Come on, Josh.
Hi everyone, my name is Josh and I'm part of the GREAT project. Unlike some of the other scientists you've learned about, I don't usually collect data in the field. I don't drill sediment cores or study fossils directly. Instead, my job is to take all of their data and combine it into computer models. A model is a tool scientists use to help explain what happened in the past and explore what might happen in the future. So why do scientists need models? Each scientist in GREAT studies one piece of the Greenland ice sheet system. We learn that Carly studies lake fossils, Aaliyah studies lake mud, Liza studies frozen plants, Nicholas studies rocks left behind by retreating glaciers, and Estelle studies tiny fossils in ocean sediments. Each type of this evidence tells us an important story, but it's only part of the picture. Did you notice that in your own stations, each one of these pieces of evidence gave you a clue, but none gave you the whole answer? My job is to come in and look for patterns that appear across all of those clues. The data come from all different places around the Greenland ice sheet and from different times in the past. Some tell us about the land, some tell us about the ice, some tell us about the ocean. Here's the thing, they don't all line up perfectly, and that's completely normal in science. I'm not looking for every data set to say the exact same thing, I'm looking for where they tell the bigger picture. Did you find that too? That the clues didn't match up perfectly, but they pointed at least in a similar direction? So when I combine all these data, what do I see? Well, when we put all the evidence together, we see that the Greenland ice sheet has changed many times in the past. There are periods when it was larger than today. There are periods when it was smaller than today. And we learn that different parts of Greenland changed at different speeds. But across all these studies, one pattern stands out. When the climate warms, the ice sheet tends to retreat. Is that what you saw in your stations? Now, how does this help us understand climate change? Well, the past gives us a way to test our ideas about how ice responds to temperature. When many different kinds of evidence point to the same pattern, scientists feel more confident in their understanding. Models help us ask questions like, if the climate warms like this again, how might the ice sheet respond? So in the end, models don't predict the future perfectly, but instead they help us explore possible outcomes and prepare for them. So how does this connect to what you all did? You all acted like scientists. You analyzed evidence, you compared different types of data, and you looked for patterns. My job's very similar, just on a bigger scale. I use computer models instead of microscopes or sediment cores, but I rely on the same scientific thinking that you all practiced. So what's the takeaway message here? Science isn't about one perfect answer. It's about building an understanding from many clues. When scientists study the same system in different ways, we learn much more than we could from just one study. And that's how we understand the Earth's past and how we hope to prepare for its future. So what you all learned here and what you saw with this evidence helps us understand how the Greenland ice sheet changed before and why scientists are paying close attention to how it might change again as our planet warms into the future.
So I think that's a really great summative piece for this particular curriculum. I think I mean, for any curriculum, frankly, about climate change, and especially when we're trying to think about the past, it really brings together a lot of big concepts, ties in modeling, really, yeah, really kind of, I think, does a great job. And and he looks just like his superhero, does he not? He's a lot of fun. Okay, so that's it. This takes us to that particular curriculum, but actually, what I think I'll do is share the next page because it's a bit of a more intuitive dive. So if you went to Lamont and you went to our education page and you go over here to polar science, each one of these curriculums is embedded in this page. So you can just go to this particular area and you'll find all of these resources. All of them are hopefully something that could be useful to you in terms of sharing some of the understandings that we've collected from these different projects and bringing a connection to current contemporary science research into the earth sciences in the classes that you're teaching. And with that, I will stop sharing. Thank you all for showing up on a Saturday morning. I hope we don't get too much snow, but enough to have fun.
Okay, I'll be
It's our
thinking of you from
pleasure.
San Diego.
Say it again.
I'll be thinking of you from San Diego.
Yeah, I'm sure you will. And Renee, enjoy your day off, right?
I'm counting on it.
All right, everyone. Thank you so much.
Thank you. This was
Thank you.
awesome.
Bye.
Thank you. Bye-bye, all.